Hello everyone. I guess everything's working. Looks like it is. Okay, so I thought that this week I would just go ahead and solve the quiz, and then at the very end I'll do a few comments sort of reviewing what we've done so far. And of course, considering exam 2 is coming right up. So let me get a little bit bigger there. Okay. Yeah, so our first question here, find the doubling time of the population of Ain't There, North Dakota, which currently has a population of 500 and is growing at a staggering rate of 20% per year. Now, the name of this is fictional, but this actually relates to various oil extraction practices that have changed the landscape in North and South Dakota a little bit. And we do have these kind of boom towns that pop up and grow ridiculously. You have people paying $1,000 a month to stay on a couch in a trailer, etc. All right, so let's go ahead and get started. So what can we dig out of this problem? So we have a growth rate here. So we know that R is, and here is where we translate into, here is where we translate into the decimal form. So 20% goes to 0.2. Okay, and then from there we know that R is going to be 1 plus that. Alrighty. And what else do we know? Well, we know our initial population, but we don't need to know it, if that makes sense. Since what we want here is the time it takes for the population to double, what we're going to do is we're going to set up the solution to our riddle. So we ask the riddle in English and we solve it in math. The riddle is, how long does it take the population to double? The answer to that is that, well, I have a cat, and there's some special t out there where this cat equals 2 times what it happened. So yeah, we could plug in 500 here and 1,000 here, but notice, no matter what your initial value is, it always cancels out when you're solving for doubling time. And this is true in general. Half-life too. You always have a half C on one side and a C on the other side, and it always cancels. If you're growing, it cancels and leaves you 2. If you're decaying, it cancels and leaves you 1/2, and that's all. Okay, so we're going to do our trick, our log app is equal to plug a trick. And I'm going to say that this is this special t that we're solving for here times the natural log of 1.2 is equal to the natural log of 2. Now we have to natural log both sides. Both sides. Both sides. Yes, okay. And so then our special t is a ratio of natural logs of some numbers, as it will always be. And if we compute that, we get something like 3.801 years. Now the bonus. Why is the rule of 70 a poor choice here? Well, the rule of 70, so what we do is we take 70 divided by R, and we express R as a percentage there. And we should get, that's about equal to the times 2 time or the 1/2 life. Yeah, but this is provided the absolute value of R is right around 10%, or right around 0.1. So it can be a little bit bigger than that, but certainly not double that. So this 20% is too big, big for rule of 70. Okay, so that's the deal with that part of that, and we're good to go. All right, so here we have 2 points, and we need to fit an exponential equation to these 2 points. So for this one, instead of thinking of an exponential equation as something completely different from anything you've ever seen before, I would like you to think of this. So think of an exponential function as just another, let's say, flavor of two parameters, one input, one output. And so what I'm doing here is I'm thinking back to linear equations, because this description, an equation with two parameters, one input and one output, hey, that could describe a linear equation. We'll see that this also describes a power function in chapter 7. So yeah, let's think about it like that. Well, if I have two parameters and I have two combinations of input-output, and I do right here, two input-output combos, yeah, then all I have to do is set them up and knock them down. For example, so you write your general form, and then you start plugging in your input-output values. So we have 524 as a point. So I'm going to take this guy, and I'm going to plug, so I'm going to take CA equals, I'm going to plug the 5 right in here, so to the 5th power, plug the 24 over here where the output goes. All right, set up the same one here. I plug in 14, I get 0.5. CA to the 14th is equal to 0.5. Okay, get a little finer here. Okay, so I can write something like C is equal to 24 divided by a to the 5th. Well, if this is true, and C is a parameter, so it takes on one value for each equation, then there's no reason I can't plug it in here. So let's do that. 24 divided by a to the 5th times a to the 14th is equal to 0.5. And we do some chapter 4 algebra here. So we'll subtract these exponents. And we find that 14 minus 5 is 9. So I have 24 times a to the 9th is equal to 0.5. Then a to the 9th to the 1 over 9th power is equal to 0.5 divided by 24 to the 1 over 9th power. And so, yeah, then we have our a. Once we have our a, take this a value, plug it right in here put it to the 5th power, of course, and we'll have our c. Let's see, I am out of room. So what I'm going to do is I'm going to come down here and then we'll solve number 3 on a separate sheet of paper. Okay, so what do I have here? I have that A is whatever comes out of your calculator when you do this. 1 over 9. It's about 0.65, either way you do it. I'm about to show you another way, and we'll get a few more decimal places doing it that way. And then C is about 206. And if you do 24 divided by 0.65 to the 5th power, you get about 206. Okay, another way, fancier way. If these things up here are equal, so if these two things are equal, and say these two things are equal, right? Then their ratios are equal, right? So if red equals red and green equals green, then I can do something like CA to the 5th divided by, oops, let's get super fancy with the colors here. How about CA to the 5th divided by CA to the 14th, 3-color equation. That's the same thing as 24. We can do better than that. 24 divided by 0.5. Oh, 2 different colors of green, darn it. 0.5. Well, if that's true, let's just do our algebra. C cancels C. And now we have the opposite we had before. Before we had plus 9. Now we're going to have a to the minus 9 is equal to 24 divided by 0.5. Here we had 0.5 divided by 24 to the plus 1/9. Now we're going to have 24 divided by 0.5. If we do minus 1/9 on this side and minus 1/9 on that side, we again get 0.65. And this time I'm confident to throw a couple more decimals on there. So dividing is a super, super nice method for these exponential equations. So either way you look at it, my favorite exp is 206. And doing by our second method, I get 0.17 times 0.6504 to the t power. There you go. So we wanted an equation. Oops, there we go. We wanted an equation that had 2 known parameters and a whole bunch of outputs that we could generate from that. So given the output, I can give you the input using these 2 parameters. But what we started with was 2 known parameters, or 2 known variable combinations. And using that, we solved for our 2 parameters. So here's that relationship we set up there. 2 parameters are 2 relationships between our inputs and outputs that got us our 2 parameters. Once we have our 2 parameters, we know we don't change. And so there's our final answer. All right, number 3, switching over. Add page below and let it be blank. All right. So we have a helium-filled balloon slowly deflating. So the information here is that during any 24-hour period, it loses 5% of the helium. Excuse me. And we start with 8,000 cc's of helium at noon on Monday. So 8,000 cc's noon Monday. And we're going to go till Wednesday night. So the way I think about this is noon on Tuesdays, that's 1 day. Noon on Wednesdays, that's 2 days. Then we wait another 12 hours. That's another half of a 24-hour period. So 2 24-hour periods plus 1/2. That gets us our 2.5. So whenever we're done constructing our equation, this is the t we're going to compute our value of interest with. So this is t. So we know we want the specific output relating to this input value over here. Okay, so how do we construct that? Well, it loses 5%. So right there, you know it's decaying. You know it's losing 5%. So you know your R is going to be minus 0.05. And that makes A, 1 minus 0.05 is 0.95. Okay. So then, then we got our C right here. We got our A right here, so we're ready to compute. So this is just a matter of CA to the T. In our case is in this case 8,000 times 0.95 to the 2.5 power. And if you run that through your calculator, let's think here. 0.95 squared. I mean, it's smaller than 0.95, not by too much. So we should expect to have more than half, right? We certainly haven't gotten to the half-life. This is small enough that we could even take that into consideration, right? 70 divided by 5 is, well, it's more than 10, right? I forgot my calculator when I went in to make this video, so incidental calculations will have to be approximate. But yeah, look at this. We know that 70 over 5 is greater than 10. So this should be nowhere near half. This means that we have nowhere near 4,000 cc's. Okay, so we've got a little piece of information there that will help us be confident when we compute this. And if we compute, we get 7,037.19 cc's. And there you go. So helium lasts a while. You kind of know this, right? It's like a week before the balloon from your birthday stops being inflated at all, right? Okay, that's the first page. Whoop. Second page. All right, so yesterday in class, we discussed the so-called rule of 70. So here I want you to explain through calculations and algebra why the rule of 70 is bad for something like a is 1/2, right? Here we have a equals 0.5. So we can go through this, right? That means decay. That means that r is minus 0.5, so that 1 minus 0.5 is 0.5. Oops, clean that up a little bit. Okay, that was, well, not the point of the problem, I guess. So let's think here. So if I was going to use the rule of 70, so if rule of 70 used, well, I would take my 70, I would divide by my r, 0.5, and we're doing absolute value of r in here, so this would be 50, 50%. So this is losing 50%. So you take the 50%, not the minus 50%. And this comes out to 1.4. Now let's do it the real way, right? So we don't have any information about what my initial value is. Actually, we do, right? I told you this was the exponential equation. Y equals 1 times 0.5 to the t. So we even know that our c value here is 1. So we can kind of ignore it. Okay, so let's go through and take the double or the half-life the hard way, right? So I don't know what, but I don't know much, but I do know that half of c is 0.5, right? So I know that there's some t out there, some special t that makes this thing equal to 1/2, right? And my c is 1, so I just get to write 1/2. I don't even have to go through the motions of canceling my c's in this case. All right, now if I just knew t, I could take the tth root of both sides, but I don't, so I'm going to have to natural log it. Well, look at this. I got natural log of 0.5, natural log of 0.5, and t star over here that I'm going to solve for. So wait, I got t is equal to natural log 0.5 divided by natural log of 0.5. Wait a minute. Anything divided by itself is what? 1. Yes. Okay, so what I wanted you to see here is that 1 is not equal to 1.4. Yeah, rule of 70 doesn't always work. Good thing to know. All right, tritium, heavy hydrogen. Star Trek fans will recognize tritium. All right, Now, we can use the rule of 70 here as long as you convince me why. The reason why, rule of 70 here. Because 0.055 is less than 0.1. Sweet. And the absolute value of it is even less than 0.1, so even better. Okay, so what do we do here? We need to find the half-life. I'm not even given an initial value this time. So what we can do is we can say to ourselves, well, I don't know the initial value. I do know A, since it's decay and it's decaying by 0.055 per year, I can say that A is equal to 1 minus 0.055, or about 0.94. 945. Okay, so let's set up our relation, right? Don't know much, but we do know that we have a cat and that there's a sum value of this cat that gives us 1/2 of what we started with. What we started up with is the same as C. So what I want you to be thinking in your head is C is what? What I started with. That is what C is. Okay, so let's plop in our value for A, since we do know that. C times 0.945 to some special t value. Whoops. Some special t value, t star, is 1/2 C. And again, we see here that when we're doing half-life and doubling time, initial values don't matter because they always cancel out when we set up the mathematical solution to our verbal riddle. How long does it take to go half of what we started with? All right, natural log trick, here we come. T star, natural log 0.945 is equal to natural log of 0.5. And T star is natural log of 0.5 divided by natural log of 0.945. And if we do it that way, we come out with 12.253. Now, if we do it the other way, so if we do 70 divided by 5.5, again, R is a percentage there, what we get, 70 divided by 5.5. So yeah, if you do that, you get 12.73. Not bad. Still an estimate, right? We can still do better. And in the age of computers, it's like, why wouldn't you always just do better? I mean, natural log's just a couple buttons on a calculator. So yeah, there's the quiz. So yeah, let's see. It does not tell me how long I've been recording. This is an interesting property of Google Hangouts. Okay, well, however long it's been, we're going to keep going for a little bit longer. So yeah. So kind of what we talked about since exam 1. So we already talked about trig. Exam 1 talked a little bit about trig. So what was it? It was exponent rules. conversions. Finance. And exponential functions. And that's kind of the exam material in a nutshell. So our exponent rules, you want to get good at those. They will probably not, the ones you're tested on will not be so complicated as the ones that have been on the quizzes. But I don't know, it seems like a good review of those rules doesn't take place unless we ask complicated questions at first. But by exponent rules, we're just talking about these kind of things. A to the n, a to the m is equal to a to the n plus m. And this makes sense because we know things like 2 times 2 squared is 2 cubed. That's 8. 2 times 2 times 2 is definitely 8. And but we can also think this is that's a 2 to the 1 there. So we got a 2 to the 1 plus 2 is 2 to the 3. So yeah, it's useful for that. What else did we talk about in here? In chapter 4 stuff, we also talked about, and so there's the cheat sheet for these on the course webpage. There's stuff in your book about them. Remember that the answers to odd problems are provided. So if you want to brush up your skills on these simplify problems, that's where I would go to do that. What else did we talk about? Orders of magnitude, right? Great way to compare big quantities. Let's see, how much bigger is a human compared to an atom, or compared to, compared to an atom? Well, you just say, well, what's an atom? About 10 to the minus 10th. What's a human? About 1. Divide. So we have 10 to the 0. Oh, so there's about a 10 order of magnitude difference, right? This one's 1 is 10 to the 0. So we got 10 to the 0 compared to 10 to the minus 10th. Looks like I'm going to have to multiply by 10 times to get back. You might want to check this value. I pulled that straight out of my sleeve, so I'm not sure. It might be 10 to the minus 15th or something. But yeah, there's orders of magnitude. Let's see, orders of magnitude, scientific notation. The key here is to remember you're just moving decimal places around. So it's like a situation where I have like 96 million, say, right? Millions are times 10 to the 6th. A little table in your book for that. So I know where to start, right? I have 96 times 10 to the 6th. But this isn't quite in scientific notation, right? We have to have the absolute value of n is greater than 1. Greater than 1. And this thing has to be greater than or equal to 1, and this thing has to be less than 10. Okay, so we're going to have to move a decimal place, right? If I move the decimal place left, I am quote-unquote dividing. So I can think about this whole thing here is I got to move this decimal place, and I can't change the value of the number. So instead, what I'm going to do is I'm going to multiply by 1. And I'm going to multiply by 10 divided by 10 equals 1. But I'm going to kind of monkey with these things, right? This is a product, so as long as I multiply once by the top and once by the bottom, I'm okay. What I'm going to do is I'm going to take the bottom, I'm going to put it over here, take the top, put it over here. So I have that 96 divided by 10 is 9.6. And I have that 10 to the 6th times 10 to the 1 is 10 to the 7th. So I put those two facts back together, and this is the same thing as 9.6 times 10 to the 7th. Some other tricks for that, count your 3's. So if I had like a number like this, 1 million, this is times 10 to the 3rd. right? Or rather, something with a 1 here is times 10 to the third. So this has to be times 10 to the sixth. Yeah. So, or we could count up, right? 0, 1, 2, 3, 4, 5, 6. And that's how it goes. Yeah, so review your exponent rules, review your conversions. Quizzes are good for that. There are several, more than several conversion problems in the book that you can take a look at too. Yeah, so what else do we do here? Finance. So check over the finance packet. But essentially there's 3 formulas. If you're talking about putting stuff and leaving it, so if that's the practical upshot of whatever verbal description you're getting, you know, I put some stuff in an account and I leave it, that is lump sum. And so these are problems like, you know, 150 is invested in account earnings, such and such, you know, $150 quarterly, say. So in that case, amount is invested. We'll give it a dollar amount. A rate, we'll call it 5%. Quarterly. So here's our R. There's our P0. This means N equals 4. So I saw a little confusion about that on the quiz. Quarterly means 4 times a year. So that means every 3 months. Some people were getting that backwards. So yeah, N equals 4. Yeah, 4 times a year is every 3 months. Okay, so putting our pieces together, our final amount after T years is going to be P. Oops, I'm already messing it up. Already messing it up. $150 times 1 plus 5%, so 0.05 over 4 to the 4 times however many years we let it get invested for. Yeah, so that's your basic lump sum. If I'm making payments, then I use the ordinary annuity formula, where A is the amount, T years. And then we have our fancy old formula, 1 plus R over N to the N times T minus 1. Oops. All of that divided by R over N. And we go for it. So, and a lot of times we want to know how much we have to save to have this amount. So if we do that, we take the top. We realize that this is A divided by 1. We take we multiply both sides by the bottom here, then divide both sides by the top here. And we end up with R is equal to A times R over N divided by 1 plus R over N to the NT plus NT here, guys, minus 1. Yeah, and so we can get the payments into account. In order to have a amount after T years. So you need the years given, right? You need to have everything but R determined if you're going to calculate your monthly payments here. All right, that's lump sum. So for loans, so this is ordinary annuity, excuse me, not lump sum, ordinary annuity. So if I'm taking out a loan, thing you want to do here is, so the formula looks like R for monthly payments is P0 times R over N divided by 1 minus 1 plus R over N to the minus MT, close brackets. And remember, in Desmos, you got to replace these with curlies, or with, with round brackets, not curly brackets. And I don't know. Probably just make sure I haven't told you a lie yet. Oh, good. No lies yet. This is indeed the correct formula for that. So the tricks here, P0 is going to be cost minus your down payment. And we've done a couple examples, I think, but yeah, that's your trick there. Cost is, or P0 is cost of the thing you're taking the loan out for minus the down payment. And that can really drop your interest rate, so it's important to have. So that's like finance in a nutshell. Conversions, I think we've done a lot of those. If there's a request, we'll do a couple examples in class. Exponential functions. Let's see. Well, that's what we've been kind of focusing on a lot lately. So it's a two-parameter. Two-parameter function, one input, one output. We talked about how for decay, so it always goes through this point C there, because we always have a cat. And if I plug in 0, then we have CA to the 0, and that's always 1. So we always end up hitting C, our initial condition, well, at t equals 0. I guess that makes perfect sense. Huh? And so our decaying exponentials sounded something like shh, and our increasing exponentials sounded something like shh. And yeah, maybe after exam 1, we'll investigate a little bit more about that. Well, we've got a little time. For example, if I put a negative c in a decaying exponential, now it's something that increases to 0, but never quite reaches 0. Likewise, if I put a negative in front of an increasing exponential, now I have something that never quite was 0, but decays all the way to negative infinity, all the way through the floor of the building and out the other side. So a little bit of shapes about exponentials. We just went over how to get one from 2 points, how to get one from a description, and so on. So I think the pattern's starting to emerge, right? We have a function to construct. So to construct the particular function for our situation, need an input, output, combo for each parameter. And yeah, so you just set up your equations and solve for your parameters. And then we have rule of 70, which I think I went over really well in this video, or at least well enough. So I'm going to say, look back and make sure you understand when you can and cannot use the rule of 70. I feel like I've been talking for a really long time, so I'm going to cut it there. And I hope you guys had a good weekend, and we'll see you in class tomorrow.